Okay, I think we'll get started. So today we're going to talk about the second and third laws. So this is the third day now that we've been talking about the laws of thermodynamics. We saw the zeroth law 2 times ago, and then the first law last time. The zeroth law introduced the idea of thermal equilibrium and temperature, and the property of transitivity, that thermal equilibrium is transitive. First law introduced the idea of conservation of energy, or captured the idea of conservation of energy, stating that the change in the total internal energy of the system must equal the heat in and out plus the work in and out of the system to the environment. All right, so the second and third laws deal with another critical property, entropy. And entropy is a little bit different than energy. Energy we can talk about even when we're in one particle systems where we have, say, a single free particle. We could talk about the kinetic energy. And even if that's the entire universe, this concept of energy is there. Entropy and temperature, for that matter, are what are called emergent properties. There's no such thing as entropy or temperature at the single molecule level. This happens only when we have a big collection of molecules. And we know that the macroscopic state is this huge collection around Avogadro's number of molecules. And what we're looking at are the average properties. Well, the average property of temperature, the average property of entropy emerge out of the fact that we have all these particles. But they're nonetheless just as critical in deciding how a system comes to equilibrium. And in fact, we will see that energy and entropy are the key driving forces in nature. And there's a great compromise in nature between trying to minimize the energy and maximize the entropy of a system in order to establish equilibrium based on the constraints of the system. So entropy is the key property here, and the second law introduces this entropy. Now, we are not able to talk really rigorously about entropy without an area of chemistry and physics called statistical mechanics, which we will not be getting much of, just some of the results, but not much of statistical mechanics in this 3-course introductory period. We will certainly have multiple courses on statistical mechanics through the curriculum, but those will be coming later after this course. So we're just going to have to take this thermodynamic idea of entropy as just being this property. This property is important enough to have a name, and we have equations surrounding it. All right, so second law is this, that this quantity called entropy, when multiplied by temperature, it has to be greater than or equal to the change in heat exchanged between the system and the surrounding. Notice work's not in here. And this is general. This is a general statement. And this is true for any spontaneous process. So in order for this not to be, we have to be doing something on the system. So for any spontaneous process or process that will just go naturally, the change in entropy has to be greater than the heat given off or taken in. Now, let's look at a couple of things that we can deduce right from this. First of all, this is an equation. So the units on this side have to equal the units on this side. So we see the units here are joules. Here's Kelvin, or temperature of some sort, and then entropy. So entropy is an energy per temperature, or in SI units that would be joules per Kelvin. Also note, greater than doesn't mean positive or negative. If this is positive, for example, then this would have to be more positive. If this is negative, this just has to be less negative than that. It could still be negative. So just remember our basic ideas about a greater than sign. When is it equal? Well, we've talked now a couple of times about this idea of a reversible process. So this would be when the system is going so that if you just put a little bit of back force on it, infinitesimally small amount, then it will stop and turn around. And we saw that in a mechanical advantage when we were a mechanical situation when we were back in one of the earlier lectures, and then we've talked about it recently in the context of a reversible PV work where the pressure inside equals the pressure outside. So when we have reversible conditions, this collapses to an equality. And in fact, this is the thermodynamic definition of entropy. So the thermodynamic definition of entropy says that a very small change in entropy is due to a small reversible heat exchange over the temperature. Now, this doesn't have a lot of intuitive appeal, and so it's just what it is in thermodynamics. And like I say, you need statistical mechanics to really get a deeper appreciation for what entropy is. Now, your book will say that entropy is a measure of disorder. That's probably what it'll say. If it's being a little more careful, then it might say it's a measure of the potential for disorder that a system has. And so that's how we want to just develop our first intuition surrounding entropy. Now that's flawed in a lot of ways, so we will be actually getting to a better definition later on in the curriculum. But for now, that will be sufficient. Okay, let's look at another special case when we're under an isolated system. In this case, the heat exchanged is 0, right? And so that definitely puts a 0 on this side, and we can divide by T, and we get this expression. And this is true for any isolated system. And this is called the principle of Clausius, which states that any spontaneous process, remember these are talking about spontaneous processes, the entropy will increase in an isolated system. And so probably in your general chemistry book, almost in every general chemistry book, there's some kind of statement that the entropy of the universe is always increasing. And that's because the universe is an isolated system. There's nothing beyond the physical universe. And so that's the only true isolated system. And so therefore the principle of Clausius must hold, and entropy increase for any process. Now, that does not mean that's talking about the entirety of the universe. So that does not mean that locally we can't have a decrease in entropy spontaneously. So life spontaneously arose. That is a very orderly process or the formation of a planet, very orderly process, less potential for disorder, reduced entropy. But what it means is elsewhere in the universe, or coupled to that process, the overall process is such that the entropy is increasing. So even though a plant can grow, cells can organize, the net result is increase in entropy, even though for the cell itself, it's a decrease in entropy. And that's really getting back to this general statement that the cell itself is not isolated, so it does not need to obey the principle of Clausius. All right, let's look at a couple of examples. Reversible heating. So let's write our reversible case now. So here the greater than sign becomes an equal sign. We use the heat capacity equation. So we get that, and then we do a little bit of calculus here, so I won't step through it, but if you've had some calculus, I think you'll be able to quickly see how if we integrate both sides of this equation, we end up with this fairly unusual looking formula, at least, if we aren't familiar with calculus, but you can see that the change in entropy is dependent on the log of the ratio of the temperatures and then on the heat capacity. So let's take a little numerical example quickly. Let's go back to that block of iron that we've been using lately. And let's say we have 3.25 grams, and we have a specific heat capacity of 0.449 joules per gram Kelvin. And let's raise the temperature 100 degrees from 0 degrees to 100 degrees. Well, now we're not talking about delta T's. We have absolute temperatures in there, so we have to be careful and make sure we always convert to Kelvin here. And when we do that, we plug everything in, and we get this answer for the entropy. And we see that this is positive. So we have increased the temperature, and it's positive. Let's see if we can get an intuition about that based on this understanding that entropy is the potential for disorder. So as we add heat to this iron, we give it more energy, and that it has more energy, it's able to access different energy states within the system, and that allows it to sort of become more disordered. And so I know this is hard to really intuit without taking a technical path to it. But when we increase temperature, when we add this energy, we increase the potential for disorder. If we were to cool the system, we should expect a decrease in entropy. So heating will increase entropy, cooling will decrease. Same is true with an expanding piston, for example. So if we have a gas and it's in a container and then it expands, that gas is free to explore more possible states, and it's more able to be disordered. And so if we have an expansion, we have an increase in entropy. A compression is a decrease in entropy. And finally, if we talk about a mixture, so if we have gas A and gas B, we mix them, then that connects more with probably with our idea about disorder. Then if they're mixed, they're going to have more disorder. So it increases entropy to mix two gases or anything rather than keep them separated. All right. So that's the second law. Let's go into the third law. Now the third law will look a little bit intimidating here because it's got this integral sign in it here. And we have to leave it in there because the heat capacity really does change dramatically with temperature when we're close to absolute zero. And that's exactly what the third law is doing. The third law is placing entropy on an absolute scale. So unlike energy, which is always on a relative scale, entropy is connected to absolute temperature, and we can integrate up from absolute zero to whatever temperature we're at and capture the absolute entropy value. Now we can't do that with energy. Energy is always relative from one state to another. It's always a delta U, for example. Here in second law, we were still relative, always a delta S. But now the third law puts entropy on an absolute footing. Now, let's interpret this. Let's not worry about this too much. Let's interpret a couple things about this equation. So what is this? This is the entropy of whatever we have at temperature T, okay? And whatever that temperature is. This is the entropy at temperature zero, absolute zero. So if we have a pure homogeneous substance, that's zero. If we have a mixture, if we have some imperfections or impurities, then this will be some residual value, non-zero value. But this is the entropy at absolute zero. Now, here, if this is going to have meaning, right, if that's going to have any physical meaning, which it does, then this must be finite. It can't be infinite or undefined. And if we look at this, we're going to be plugging in a t equals 0, and there's a t in the denominator here. So that means, that implies that in order for this not to give us a value of 0, this heat capacity better be going to 0 faster than T does as T goes to absolute 0. And that is indeed the case. The heat capacity goes to 0 at absolute 0. And that's a really weird situation. And in fact, it implies that we can never actually get to absolute 0. And so we get very, very close. We've gotten to very, very close to absolute 0, but we can never achieve absolute 0. And it's for this reason. If the heat capacity goes to 0, right? We said, what is the heat capacity? We learned about that last time, or 2 times ago. Heat capacity is the ability for the system to hold heat, or to accept heat energy without raising the temperature. So it's this resistance to temperature change when we add heat. Well, if that goes to 0, then even the slightest fluctuation of heat, which there always will be, is enough to kick up the temperature infinitely fast. Now, that doesn't mean the temperature goes off to infinity. It just, the rate of change of temperature with pushing heat in is infinite. Then very quickly, the system will get some temperature. The heat capacity will no longer be 0, and then that will stop happening. But at absolute 0, because the heat capacity is 0, we can never actually get to absolute 0. And that's a consequence of the third law. All right, so we have worked through all of the laws. Let's summarize them here in a table. 0th law is dealing with thermal equilibrium, the property of transitivity of the thermal equilibrium. Property is temperature. Phenomena is transitivity. Property is temperature. First law, dealing with conservation of energy, and the property is total internal energy. The last 2 laws are dealing with entropy, the introduction of entropy for the second law, and the absolute entropy for the third law. And as I mentioned in the beginning, energy and entropy are nature's great driving forces for what will happen. And so we will see in maybe in a couple of weeks that there's a great compromise in nature, trying to minimize energy and maximize entropy. And where it finds that compromise is where equilibrium occurs. Now, we have to do a few things before that. We're going to dig into chemical reactions and learn a lot of the things that we should know coming out of general chemistry. So we want to take a little bit of time to capture some of the details associated with chemical reactions. We also have to define a couple of new functions, enthalpy and free energy. It's free energy, actually, that will be the key to capturing this great compromise in nature. And we will develop something called the free energy equation for chemical reactions, which govern the behavior of chemical equilibrium, which is a really important part of this Introduction to Physical Chemistry 2 course. All right, so that's what's to come. There isn't a lot of homework to practice on this. Just look in your book at these sections. These will be both in your physics book and your chemistry book, no matter which ones you have. Try to pick out some problems, work those, but mainly keep telling yourself the story of this, right? We aren't ready to do anything really, and we haven't gotten the full, high-level picture, but you want to start to internalize some of this so that when we do get to that big picture down the road, or when we do have to start talking about what's going on in an actual chemical reaction, you'll have some grounding for that.